on OURVL, that are linked on OURVL. Anybody? How many of you might think, what videos? All right, I appreciate your candor. All right. So on Monday, we talked about peer-to-peer networks, peer-to-peer applications, I'm sorry. So we talked about some of the issues that surround peer-to-peer applications, the fact that you have need for some complex management protocols because peers come and they go. We also talked about some issues with running peer-to-peer applications, especially behind NAT boxes. We mentioned Skype, for example, right? What was one issue with a NAT? You cannot open a connection, an inbound connection to a host that is behind a NAT unless you've basically punched a hole in your NAT, right? You've enabled port forwarding. So Skype, what does Skype do? Anyone recall? Any thoughts? Anybody? Sorry? What does Skype do to get around the problems of running behind the NAT, for example? Because say someone is trying to call you, if you're using Skype, if you're behind the NAT, that person cannot have a connection open to you. So what does Skype do? Let me see your notes, see what you actually do. Thank you. What's that? Can you go? What's that? Oh. Unless I got carried away then. I obviously got carried away. Siobhan corrected me and said we stopped to circulate the HTs. So, all right. Maybe that's why I couldn't answer the question. Thank you. Okay. Let's see if I finish up all the content. All right. We talked about BitTorrents as well, right? What happened? What's the idea with BitTorrent? You guys use peer-to-peer sharing. Okay, peer-to-peer sharing of files. Okay. So what happens? Give me the names of some of the parties when you're using a torrent. What else? Peers. What's that? Peers. Okay. And actually, the seeders are also peers. Okay. What else? There's a what? It's normally leeches, because I didn't hear you talk about that. Leeches are also peers. Right? The seeders, the leeches, they're all peers. We just call them leeches because we feel they're not doing enough to support the network. Okay, but what else do we have? We have a tracker, right? And what's the role of the tracker? Okay, so I have a list of peers that are participating in the torrent, right? So let's say Alice is trying to get a file via torrent. So Alice joins the torrent. Then what now? Now what?
start receiving chunks of files from other users.
Okay. All right, fine. Alice will start receiving chunks of the file from other users. How would that happen? How would Alice get her first chunk? By the way, you guys know that
you request for errors.
Okay. That the very first chunk that Alice, okay, the chunks that Alice will request initially will be the rarest in the kernel. But what about the very first chunk that Alice is? Any ideas? Back in the technical. Okay, what's optimistic on choking? What is optimistic on choking? Also in the notes. I know that. Yes. It can happen, but what happens before that can happen as a result of optimistic on choking? But what's the key idea with optimistic on choking? Somebody randomly starts sending you chunks. Okay, that's actually how Alice will get the very first chunk. Okay, Alice joined. Somebody would have randomly just sent her a chunk. Okay, she would get a chunk. Okay, and then Alice, for example, will start requesting the chunks that are rarest in the torrent. Why do that? They become less rare, right? Other people who can get them. Okay, and you get the file a bit quicker too, right? Let's just say you have a handful of people with that rare chunk. If they disappear, then what? You're just out of luck, right? So it's better to get the rarest one. Okay. Then we talked about distributed hash tables, right? And the fact that with the distributed hash table, you have you basically have these key value pairs, okay? And peers will query the distributed hash table with the key, and peers can also insert keys. So in the worst case, if you don't have any shortcuts, you're basically going to have to go n times, make n hops around your distributed hash table, okay? And so we could get around that by implementing shortcuts. And if you choose your shortcuts well, you can actually cut down your lookup time so that it is, you can get, big O of log n messages to answer your queries. Let's see. I think that was that. Okay. Okay, so good. Thank you, Siobhan. Now this is where we did end. So when we are handling peer churn, what we'll do is make sure that every node knows it's two successes basically, and periodically a peer would ping its successors to see if they're still alive. Now let's say that peer 5 leaves abruptly, right? So peer 4 would know that because peer 5 is not responding, and so it can then set its next successor to what? 8, and then it will ask 8 for who its next successor is. Okay, who 8's successor is, immediate successor, and 8's immediate successor, that's 10, will now become 4's next successor or second successor. Okay. All right. Now let's say peer 13 wants to join. Where would peer 13 join? Where would peer 13 join? Okay, between 12 and 15. Okay. So now tell me what would happen here. Peer 13 wants to join. Okay.
Peer 12 will make 13 to be successful and 13 to be.
Okay. Remember, we're keeping track of what? How many successes are we keeping track of per node now? 2. Okay. So first 13 wants to join, that message gets forwarded around, and so 12 then realizes that 13 will become its successor. Okay. 13 is 12 will be 13's predecessor, and then 13 is then told that its successor is 15. Okay, and then peer 12 will send this information to peer 13, and it now joins the distributed hash table. Okay, I think because I made a recording of this that I got sidetracked. That I thought we had finished this. Okay. So Skype is inherently peer-to-peer because now we have pairs of users communicating. But you also have some client-server pieces to Skype. So Skype is actually a proprietary protocol, but I think it was Jim Kuros with a grad student actually inferred how it works by doing some reverse engineering. You have a paper on that. So you have a hierarchical overlay with this notion of supernodes. So with this now, you're going to have an index that will map usernames to IP addresses, and this is distributed over the supernodes. And so you have Skype clients, and you have these supernodes, okay? And you have a bunch of supernodes, and then these supernodes talk to each other, and then you have a Skype login server. Okay. So there is a problem, as I mentioned, when Alice and Bob are behind NATs. The NAT will prevent anyone outside from initiating a call inside. They have to do something special. But what Skype does is it basically chooses a relay node. Okay, so whenever a user logs in, I log in with Skype, I will actually initiate a connection with a relay node. Okay, so when now I have a connection open. Then say I have an incoming call. Okay, then my client is basically instructed to route that call, open up a connection through some supernode on the Skype infrastructure. Okay, so say Alice is told open up a connection to supernode 15. Okay, and Bob also opens up connection to supernode 15, and then their call gets routed through there. Make sense? Yes, it's going to be like a relay node there. Okay. Remember, the issue is that when you're behind a NAT, you cannot, open up someone can't open up a connection to you. Hold on a minute, let me. Microsoft is actually in the process of changing the Skype infrastructure finally. And by the way, these supernodes you can have problems with them. When I just came to Jamaica, like 2010, there was a period where Skype was down for like a day or something like that. And the reason it was down for that period was because a bunch of these supernodes went down. Okay. Microsoft actually gave people a few, everybody got a few dollars of credit if you to make calls. Okay, now that was historical Skype infrastructure. Skype is changing. This is from 2016, but basically Skype historically was based on a peer-to-peer model, and now they switched to a client-server model, and this explains why. Okay, so back in 2012, Skype already had 10,000 company-hosted supernodes. Okay, so anyway, I can I'll post this on OERVLE for your benefit. If you want to read, you can read it. Okay, so you can at least get a sense as to Skype's modern architecture. But historically, that was how Skype was set up. Okay. All right. Other questions? Any questions? What's that? The supernode is able to, okay. Supernode isn't able to get behind the NAT directly. What happens is that when the user logs in, right, then they're basically instructed to connect to a supernode. Okay, so again, it's still the user initiating the connection, right? When you're behind a NAT, you can open up a connection to pretty much any host as long as it's not behind a NAT, right? So it's the user that opens up the connection. It's not the supernode opening up the connection to the user behind the NAT.
So the user passes the message to the supernode and it passes it to the other user.
Exactly. What's that? Well, remember what I started off by saying, though, that you're going to have a hybrid architecture with Skype. It's not pure peer-to-peer. There's some hybrid parts. But it's a valid point you raise, right? But you're still having users communicating directly. And remember, all of these things are really hacks. We understand a lot better how to make things work, but now with NATs. But I remember when I was an undergrad like you, I used to use instant messaging, and once I got what was I using? MSN Messenger at the time or something like that, and I logged in, and I obviously didn't know enough about networks at the time, and I said I got the message saying we can't run this because we're behind a NAT. Anyone ever seen a message like that? No. Why? Because we have better understanding, programmers that is, of how to operate behind NATs. Right? And that's part of the reason why we have courses like this. Right? You guys get exposed to these kinds of things. You're building your applications. You have certain considerations now that you should be aware of that you can build into your application. Right? And not have an annoyed user. Okay, so now I want to talk a little bit about video streaming and content distribution networks. Okay, so video streaming. Video has turned out to be the major consumer of internet bandwidth. In the United States, I think it was 2015, we estimated that Netflix and YouTube were consuming 37% and 16% of downstream residential ISP traffic. So 53% of the bandwidth is consumed by these two streaming video websites. Amazing, if you ask me. There are, at the time, there were over 1 billion YouTube users and about 75 million Netflix users. So there's some issues with this, right? The issue of scalability. How do you reach, say, 1 billion users? A single mega video server won't work. Why not? Why won't a single mega video server work? Exactly. Right? It's a single point of failure. And then the other thing too is that, guess what? The things that are popular, say in Jamaica, are not necessarily the same things that are popular, say, in the US. Right? How many of you realize, for example, if you travel a bit, you may realize, say you log into YouTube here, your landing page is quite different from what you might see, say, in the US. Notice that? Right? A lot of the things, if you log into YouTube here, would be US specific. It's not US, Jamaican specific. At least I noticed that. Right? There's lots of dancehall videos that I could care less about. They show up on my landing page. Right? There are certain challenges with heterogeneity as well, because you have different users with very different capabilities. You know, wired user at home, right? Say you're on Digicel's fiber to the home service. You're getting a completely different user experience from a user that is using Digicel's 4G service. Okay. and whether the user is bandwidth rich versus bandwidth poor. The end result is that we have a distributed application level infrastructure. By the way, these are some of the streaming video and CDN. So YouTube, Netflix, Hulu. You guys, anyone here use Hulu? No? It's not available here. Well, yeah, but I know you guys travel too, so. Or some of you also use these services behind with VPN. So at least you try.
Yeah, it detects that you're using a VPN.
Netflix detects that you're using a VPN. Akamai, this is some Chinese, I think that's CanCan. All right, so multimedia video. Video is simply a sequence of still pictures that are coming by at some constant rate. Okay, often 24 images per second. Often. Sometimes it's better than that. And a digital image is simply a two-dimensional array of pixels. And each pixel is represented by bits. Now, one of the things we do is coding. Okay, and this is this is now we're going into a discipline called information theory. So it's not like the coding of a computer that you might program that you might. But with the coding that we do in this case, we're basically looking for redundancy within and between images. Okay, so and when we do that, we can now we find that redundancy. We can actually compress our images. By the way, just out of curiosity, let's say we have an image 1024 by 768 pixels. Okay, and let's say you have 4 bytes per pixel. Okay, so how many bytes would you need? Or let's say how many bits would you need just to show that without compression? Yes. Tell me the answer, man. What's that? Do it. Tell me the answer. Say we have an image, okay, that is 1024 by 768 pixels. Okay, 4 bytes per pixel. But how many bits would we need? So you guys can tell me. What's that?
25 million.
25 million? Okay, that sounds about right. Wait a minute, let me try something. What's that? Do I have? No, I do. Oh, and that's in bytes. Oh, oh, thank you. 4. Okay. No, it's sorry. 1024. Yeah. Okay. So this is about how many. Let's just do bytes first. Byte. Let me do bytes here first. Okay. So that's about how many bytes? Just one image without any compression. So how many bytes? It's about 3 megabytes. Okay. And we're going to need, without any compression, we're going to use about what? I think that's 25 megabits without any compression. Now, let's say you're playing 24 of these pictures in 1 second. How much data would you need? Look at how much data we're going to, our data rate we're going to need. It's about what, 6, let's see. So I see 603 million, 603 megabits per second. Anyone have that kind of data rate at home? But you guys are able to watch Netflix and YouTube, right? So what's going on? What's that? Compression, okay? Yes. So we do some compression. We do compression spatially, that is within the image, and temporally, that's from one image to the next. So here's an example of 2 images. Okay. So instead of sending n values of the same color, all this purple, just send the color purple and the number of times repeated. Right? Kind of nice. You do the same thing with the black. Now, that's so spatial. And then now, from one frame to the next, can you even tell the difference between these 2 images? Probably not. But so what you can do is, instead of sending all of frame I plus 1, you can just send the data that shows how frame I plus 1 has changed from frame I. Make sense? Now, remember, how many? Oh, okay. How many? There are these, I call it games for children, where you can draw pictures and then you flip, a book very quickly. And you guys try that? Yeah. Yes. And okay. And what do you notice? Sorry. What's that? Each one is slightly different, and if you do it fast enough, it almost looks like it's moving, right? Now, what you're doing now with the temporal coding is just making sure, instead of setting, the complete difference, okay, the complete picture. You say, oh, this picture has changed from the previous picture by moving this, widget, so many, so many spaces, horizontally, vertically, or whatever, right? So you encode those changes. And so it makes your picture a lot smaller. Okay? So now, when we're doing multimedia video, we can have either constant bit rate or variable bit rate. Constant bit rate, your video encoding rate is fixed and just send out pictures. So like what the example we worked out here, where I was just looking at, let's say we're sending out, these pictures, and we need 10.4 by 768, and so many bytes in an image and so on. Assuming we would send that out, we could have a constant rate, right? But another thing which is quite common is actually to use variable bit rates, because your video encoding rate will change as the amount of spatial and temporal coding changes. Okay, and so MPEG-1, as you use with CD-ROMs, can support rates of 1.5 megabits per second. MPEG-2 with DVDs, you can support about 3 to 6 megabits per second. MPEG-4, which is often used on the internet, supports data rates of about 1 megabit per second. So like when I create recordings, like this Zoom recording that being made of this class, when it gets saved, it actually gets saved as an MPEG-4 file. Okay, and it takes a while. Like we'll be here for maybe close to 2 hours. It'll probably take about 10 minutes for my computer to encode that file into this format. Okay, the raw video that it's taking. Okay, and I have an i7 processor with lots of RAM, but gives you an idea of how much time is involved in these kinds of things. Okay, so to stream stored video at a very simple level, we have a video server and we have a client and internet. Okay, and our stored video is over here, and we get it across the internet. Okay, let's not deal with how it gets here for now. Let's just say it's there. Okay, so one of the things that has emerged in the last 5-6 years is this notion of dash, dynamic streaming over HTTP. What happens is that you're on the server. The video file is divided into multiple chunks, okay? And each chunk is stored and encoded at different rates. How many of you have uploaded a video, say, to YouTube or something like that? One, okay. What's the process like? What's that? Okay, you upload the video, okay? Okay, it takes a while, okay? And why, okay, so let's say some of the reasons why it takes a while actually is because of your our asymmetric data rates, right? And let's say you have good bandwidth, goes up relatively fast. What happens next? After when you're up, yes, the file gets uploaded, then what? If you ever 10 times actually move that process progress file. Anyone recall what this says? You also. You don't look at it that way? Anybody else? It tells you it's processing, actually. What do you think it's doing while it's processing? What's that? Yeah, it's doing some encoding. It's actually doing some of this, where it's encoding into different data rates. How many of you have actually gone through and changed the quality of your image, your videos on YouTube? How many of you are aware you can do that? Okay, good. Okay, and so what do you notice sometimes? Okay. Exactly, right? And so what happens is, especially when you have videos, and this is more common now, when you have a poor connection, actually YouTube sometimes just determines that and starts giving you lower quality video. If you have a good connection, it actually starts giving you higher quality video. But so what happened? The chunks are stored encoded at different rates, and then there is a manifest file that will provide URLs for the different chunks. Now the client, so you're using YouTube for example, will periodically be measuring the client to server bandwidth, figures out how much bandwidth you have, and then it checks the manifest file that it got from the server and says, oh, well, my connection is poor right now, so I'm going to request a lower quality video. Okay, maybe a few seconds later, does the same probe and realizes, oh, well, over the long term, my bandwidth, link rate has gotten, connection speed has gotten better. I can request a higher rate file, and you notice, your image gets a little sharper, and so on. So basically, it consults your client, consults manifest file, requests one chunk at a time, and it chooses the maximum coding rate that is supportable given your current bandwidth. And you can choose different coding rates at different points of, in time, depending on what bandwidth you have. Okay, so Dash is a case where we put intelligence at the client. Okay, now it's the client that determines when to request a chunk. Okay, what encoding rate is going to request and where to request a chunk. So one thing that happens with video, I think I tried to make this point earlier, we end up playing out these frames at a constant rate, 24 frames per second or something like that. Okay, so ideally, you fill up your buffer to a certain point and then you start, playing out and more videos coming in. So we want to ensure, that we're requesting the chunks so that our buffer doesn't empty out, okay? And we also want to be requesting the chunks such that our buffer doesn't fill up so much that we have to drop it back. Okay, so there's some kind of balance. We also choose higher quality when there's more bandwidth available, lower quality when we have less bandwidth available. And then we also have the ability to choose our chunks from different servers around. So maybe we can choose something from a server, I don't know, in Miami or something like that, okay, versus one in LA or something, okay? So when to choose to request a chunk, you can request it from one that is close to the client. Now, another idea that is quite common with networks today is the notion of a CDN. How many of you are familiar with Akamai? Akamai? How many of you have seen that? Nobody? It's just yeah. But besides that, anyone else have seen it? How many of you actually pay attention to the URLs that you see when you're downloading things? What's that? Or using Facebook or whatever. Actually, pay attention next time. You will probably notice in some of the URLs you see an Akamai, -CDN or something like that. Okay. So content distribution networks, Akamai is one of the really big ones. It's, I think, headquartered in Boston, but they have servers all over the world. Is how do we stream content, okay, from millions of videos to hundreds of thousands of simultaneous users. So one option is you can build a single large mega server, and we all agreed that this is a bad idea because you now have a single point of failure. It's also a point where you can have network congestion. You can have a long path to distant clients, and you're going to be sending multiple copies of the video over an outgoing link. It just doesn't scale. So another approach is to serve millions or multiple copies of your video at multiple geographically distributed sites using a content distribution network. So there are two approaches. One is the enter deep approach, which is used by Akamai. They push their CDN servers deep into the access networks. Okay, and so you might have some. They're located very close to points of presence, and so you're close to users, and you have them replicated around the world. So Akamai has about 1,700 locations around the world, Or you can have bring home, where you have a smaller number of clusters, okay, in these points of presence. They're near but not within access networks, okay? And Limelight uses this approach. So let's see. Let's see if we can pull up Akamai, and we can see if we can see there. I was looking for see if we could find locations of the CDNs, but but you can go browse. This is Akamai's site. You can actually browse and see what the CDN services. Akamai claims they serve over 30% of the web traffic in the world, and they're using software as a service. Okay. Not quite, but we're actually going to do a case study on Netflix. What something like Akamai is used for often is used for pushing out updates and so on. When companies want to, if I recall, for example, Amazon used to use Akamai to push for downloading Adobe Acrobat and so on, and all these Flash players. If I remember looking at the URL, you probably have an Akamai CDN on it. Okay, so that's how these end up getting used. Netflix actually uses CDNs as well. Okay. Yeah, Netflix will use a CDN. Yes, Akamai is a CDN. Okay. If you here. So for example, this is a marketing thing, obviously, about CDN, but Akamai is basically saying most operators today are finding that a CDN solution is fundamentally necessary. What's that? Then there are CDN services. Okay. All right. So Akamai has over 100,000 servers in over 1,000 clusters in over 1,000 networks in more than 70 countries that are serving trillions of requests. Okay. So let's see Netflix now. So let's say you guys like Mad Men? Mad Men. What's that? What's that? You didn't know what it was? Oh, she didn't know. Oh, that's fine. She has her head in her books, obviously. I've never watched Mad Men actually. It could be any show that you want. But okay, so Netflix will store copies of this thing, okay? And these are actually stored around the web in different places, okay? So a subscriber then will request the content from some CDN, and that subscriber will be directed to some nearby copy. It will retrieve the content, okay? And so you basically say, where's Mad Men? And Netflix sends you a manifest file, and that manifest file tells you basically where you can start requesting your chunks. Now, in doing this, Netflix is going to figure out where their closest server is, okay? And then allow you to get data that tell you, and so you'll be basically directing your request to servers that are close to you. So you can potentially choose a different copy if the network path is congested. So this is basically said as doing something over the top. You're doing it over the top of existing networks, okay? So we have internet host communication as a service. So certain challenges with over the top. How do we cope with a congested internet? Which CDN node do we use to retrieve content? How should viewers behave in the presence of congestion, and what content do you place in which CDN node? Out of curiosity, let's deal with that first question. Yes. Well, it was so okay, you guys sometimes follow these things on the news. So HBO had their servers hacked, and people stole copies of the upcoming season of shows. And what they were doing in that case was that whoever did the hacking was requesting a ransom. Sorry? Yes, they were trying to extort them. They went, in that case, it wasn't getting copies on CDNs. So when a studio shoots a show or whatever, movie, they have a studio master copy. That's typically of very high resolution. And with that studio master copy, they then, prepare copies. Maybe they're going to, put on DVD so they can sell a CD. People don't do that as much as they have other copies which they would sell off to for license to like Netflix, and then Netflix will take that and ingest it. We'll actually talk about how that process goes. So what was actually stolen was a studio master copy, not the CDN. Okay. But let's look at this question. Where might you place content in a CDN? Which CDN node? Out of curiosity.
Nearby.
Exactly. Depends on what people nearby might watch frequently. Okay. So I started off talking about the YouTube example. Right. You notice sometimes you get on the YouTube landing page and the content you see is very often Jamaica specific. Right. It's true. I am going to pass on some videos, basically. Not videos. These are, I'll pass this on. I went to a conference, SIGCOM a few years ago. Netflix was there, and they did a demonstration. And they talked a little bit about their infrastructure. One of the things Netflix does, they have actually built servers. You guys can see one of these here. And they basically are willing to go and sign agreements with ISPs, and they will basically implement, put that in core of your network, the ISP, the access network, that is, and they remotely manage that machine. And they have SSDs on there, and they put maybe the top 20 movies that are popular in that region. And of course, they're managing that, they're monitoring that. And so they swap out the videos off and on. Not downtime. Not that many people say are watching videos right now. So it's a good time to be, replacing that kind of thing. But they implement that. Okay. And then viewer presence in viewer behavior in the presence of congestion. So I think one of these has a chart. Yes, that one. But what's the essence there? So what's that? Here, let me draw it here, and then I'll put it back. What's that? All right, I'll draw it on the board. I was looking for the shape within OneNote. By the way, can you guys all see what I'm drawing? You can think of a triangle. Okay, I realize the people at WJC can't see, unfortunately. I'll have to figure out a way of getting this. But you have on one axis play delay. Okay. On another axis, you have stability. Another point, rather. Okay. And the other side, you have quality. So the idea is that you have to users all have different things that they want to do with all of these things, right? So like when I was at this conference, this lady from Netflix, she was like, so what do you prefer? You know, do you want your video to, you sign on, you click on the link for, say, some movie, you want it to play quickly? Do you want it, you know, to take a while to start, but you have an excellent, higher quality video? You want your video to freeze sometimes, right? All of that. Yes, adjusting different parts of these things. What's that? Exactly, they're constraints, right? And so maybe you don't want your video to freeze, right? But what you're trading off, you know, this and that. There are different places where you go. Okay, so how do viewers behave? And they have to be constantly monitoring these things, you know, focus groups and so on. What CDN node to retrieve the content? What's that? It sounds like what? Yes, it is. Yes. Yeah, that lady got the PhD in networking from computer science from Stanford, and she went to work at Stanford. And so she gets the ability to watch all kinds of movies. Okay, so let's look at say how Netflix can work. Okay, so let's say Bob requests some video from HTTP netcinema.com, right? /6y, whatever. So that video is stored in a CDN at http://kingcdn.com. Okay, all of that. So Bob will then get the URL, okay, for the video from netcinema.com's webpage, and then he will resolve that by his local DNS server. Okay, so the local DNS server will interrogate NetCinema's DNS server, and it will now be told, hey, you want netcinema.com, right? That URL, well, go to kingcdn.com. Okay? And so now we go to kingcdn, and you're going to get the IP address of the kingcdn server that has the video, and now Bob can finally start getting the video from that King CDN server. And that's coming down with Dash. Okay? Are we all together so far? Yes? No? Let me turn on the light. Okay. So I promised you that we will look a little bit at Netflix and how they do things. So here is Netflix. Okay. So Netflix has its accounting, its own registration and accounting servers. So Bob has the ability to manage his account, right? You know, you can pick your which movies you like and so on, which genres and things like that. They also monitor what you watch and what you like, and that influences your account. Okay. Now, Netflix is interesting in that it has built it. Originally, Netflix mostly used Amazon Web Services, okay, Amazon Cloud, and it also used other CDNs. But now Netflix is also building its own service, as I showed you in these figures. So Bob will browse and get some, Netflix. Look at the Netflix video, find something he wants to watch. Maybe he wants to watch some episode of Mad Men. So he gets now a manifest file from Amazon, the Amazon Cloud. Okay, and that manifest file is returned for the requested video, and then Bob can start talking to the CDNs. Now, when Amazon Netflix gets a new movie that they want to upload to their library, they take that movie, a studio master copy, that is. By the way, the studio master copies are also the same copies that you would have in being sent like movie theaters. I don't know about Jamaica, but I know, for example, in the US now, you no longer have any film. All the movies are distributed to the movie theaters digitally. Anyway, what's that? Okay. So they would get those studio master copies and ingest them using Amazon's infrastructure, and then load those copies, which are encoded at different rates. Okay, so you might get the same thing and encode it at a rate for someone watching a video on a phone, one on a tablet, right? You can even do 4K HD these days, right? So you have it encoded at that rate as well. So you may have 6, 7 different encodings of the movie, okay? And then they place them on different CDN servers, which they can then use. And that's where you're basically getting your content. It's actually quite fascinating to see. So this, again, this is same conference. They showed a brief history of encoding on Netflix. In the first generation, they ran in an in-house data center, and they supported a proprietary codec, and they had just a few thousand titles. The second generation, they went to Amazon EC2, and they had support for various encodings, and they now have the ability to support tens of thousands of titles, but they had some issues. They had very long encoding times. It could sometimes take 10 to 40 times the play time just to encode, give you an idea. It was very hard to detect and localize issues, and anyway, even if they couldn't scale, basically, for Netflix. Why that's an issue I think I've mentioned here, you guys should be aware of scalability issues, okay? They keep coming up in computer science. When you guys are going to do your group project, one of the things you'll be asked is scalability concerns, okay? You guys will not have mastered it by the end of your program, but start thinking in those terms, right? The people who take part in the programming competition, one of the things they are learning, for example, is about scalability issues, because sometimes you get the problem and you have to be able to answer 10 billion queries or something like that. Right? You know? What's that? Yes, 10 to the 500. Yes, that's. Yeah, I remember seeing that. But so you do have to think in terms of scalability concerns. The third generation of Netflix encoding still used Amazon Elastic Cloud Compute, and now they started using Linux tools, and it was able to support 4K video. Everyone here see this as well? Yeah, so okay. And so they have, their pipeline. They can get the video source, inspect it, encode it, package it, deploy it. So you can do that. But that brings to an end this slide. Netflix is, like I said, it's very fascinating because it uses a lot of the concepts that we've spoken about. Okay, CDNs. They basically make use of Amazon's cloud computing. Okay, like I said, originally they didn't have that much infrastructure of their own. That has changed now. They have their infrastructure, but they still rely heavily on the cloud. Yeah. At one point, they were using not just they were using Livewire, I think. I forget the names of all the people they were using. So Netflix, okay, when Netflix first rolled out video streaming service in 2007, it employed 3 third-party CDN companies to distribute its video content. Netflix has since created its own private CDN from which it now streams all of its videos. Netflix still uses Akamai to distribute its web pages, however. And so to create its own CDN, Netflix has installed server racks both in IXPs and exchange points and within residential ISPs themselves. Netflix currently has server racks in over 50 IXPs. And there are also hundreds of ISP locations holding Netflix racks. Anyway, I remember I read that, but Netflix actually uses Akamai, as we saw. It also uses like Livewire and so on. Okay. So, Amazon. Okay. So, all right. Any questions? Comments? Okay. So we've finally finished studying network applications. So we looked at client-server architectures, peer-to-peer architectures. Looked at reliability, bandwidth, and delay in terms of service requirements. Then we looked at HTTP, FTP, SMTP, and POP, DNS, peer-to-peer networks. Looked at BitTorrent and distributed hash tables, and then looked at how all these things get tied together to do video streaming. So now we are going to basically start looking at the transport layer, which will take us about 3 weeks or so. Yes, and that's where you guys get your first programming assignment. I think you guys are dying to start programming, right? What's that? What's that? What did you say? You just started coding? Okay. So now let's start talking about the transport layer. Okay, and it's material from all of these places. And so by the end, I want you guys to be able to describe the operation of reliable delivery protocols, list of factors that will affect performance of reliable delivery protocols, and then implement a simple, reliable transport protocol. Okay, so you guys will actually implement that, transfer files, add, build, or let me put this. You're going to build a reliable protocol on top of UDP. Okay. Okay. So by way of review, the transport layer basically allows for logical communication between application processes that run on different end systems. Okay, on the sending side, it takes data from the application layer. Okay, those messages, puts them into segments, passes them to the network layer. On the receiving side, you get the datagrams from the network layer, pull out the segments, okay, and then reassemble them into messages, passes them onto the application layer. On the internet, you have more than one transport layer protocol, but the two main choices are TCP and UDP. There are other protocols, but we don't see much use of them. Why not? There are other transport layer protocols, but we don't see much use. Why not? What's that? Actually, TCP works okay, but it works well. Well, TCP, there are many ways TCP could be improved. I mean, it's quite a, it says something about TCP engineering that TCP is actually a protocol that is over 30 years old. And we're still using it. Okay. But the main reason for why the other protocols haven't seen much success is, what's that? Well, actually, not quite, but you're onto something. Because of NATs. Okay, our NATs are, expecting TCP and UDP, and they know exactly what to do and what to rewrite. So they see another protocol, it's like, what do I do here? Okay, so there are certain issues. Like there is an enhancement, a protocol that improves UDP called DCCP, Datagram Congestion Control Protocol, but no one is using it. Okay, even though it's an improvement. All right. So the network layer allows, this one by way of review, we've seen this before, allows for logical communication between hosts, whereas the transport layer allows for logical communication between processes. The transport layer will rely on the services that are provided by the network layer and enhance them as well. Okay, there was this analogy that we used in net-centric computing, which I'll use again. So let's say you have, what's that? Yes, the house and the cousins, the siblings. Right, so the hosts would be like the houses where these kids live in. Right? We can think of ourselves here as processes. Right? Each individual person is a process. And so these children inside the houses can write letters to their cousins in other places, right? Those letters that they write are like application layer messages. Okay, let's say in each house you have one cousin that's in charge of collecting all the letters from the siblings. Okay, that cousin is going to be like the transport layer as far as the cousins are concerned, and then that cousin will rely on the postal service to deliver those letters to the other house. Postal service like the network layer. So TCP allows for reliable in-order delivery and congestion control. We're going to spend a lot of time talking about congestion control. It's actually one of the top 10 topics in networking that are really quite gone away. Talk about flow control, connection setup, and you have UDP, which supports unreliable, unordered delivery. It's really a very small header, UDP, just adds 8 bytes of header on top of what IP does. Okay, and you don't have any service guarantees or any delay guarantees or bandwidth guarantees. Okay, any questions? So if I talk about demultiplexing and multiplexing, what does that mean? Demultiplexing. Most of them have controls. Demultiplexing. Okay, let's take multiplex. What's that? Yeah, at the hardware level, that's what the multiplexer will do. Okay, so but in the context of networking protocols here, what do you mean when you talk about multiplex? What's that? Gathering the chunks of data. Okay, then what? Okay, so we basically get the data, okay? We add the transport layer header. That's really all it is. And the transport layer header would include the ports at the minimum. There are other fields, but we'll add those. And demultiplexing, we look at the header information and then we direct to the correct port. Okay? So that's that. Okay, let's do a bit of review. Say we're using UDP. What do we use to direct something to a port? We're using UDP. What do we use to direct something to a port? Okay, what port number? Why? Sorry? Or not the port, sorry. Socket. What do we use to direct something to a socket? Why do we use to direct something to a socket? A port number is certainly correct. But what do we use to direct something? So let's say you have two UDP segments that have the same destination port number, same destination IP address, different source IP, different source port numbers. Will they go to the same ports or different ports? Two UDP segments have the same destination IP, same destination port number, okay? But different source IPs, different source port numbers. Do they go to the same port or different ports? I hear two people saying they go to different ports, okay? Any other thoughts? I'm asking. And then you justify your choice, your answer. Same destination IP, same destination port. But different source IP, different source port numbers. Or using UDP. Sorry? Same, well, that's the socket, same socket. Okay. All right, they do indeed go to the same socket on the destination machine. Okay. All UDP uses to identify a socket is the destination IP, destination port number. Okay. Now, TCP, same scenario. Okay, but now we're using TCP. So we have two segments that have the same destination IP, same destination port number, but different source IPs, different source port numbers. Same socket or different sockets on the destination machine. Sorry? Different sockets, correct. Why? Okay, so what things does TCP use to identify a socket? Source and destination what? Okay, so TCP uses a 4-tuple to identify the socket, okay, the source IP, destination IP, source port, destination port number, okay? So all four of those things have to be different, okay, for you to go to a socket. By the way, at any one point in time, that combination of the source IP, source port number, destination IP, and destination port number is globally unique on the internet at any point in time. If you could miraculously gather all the datagrams that are floating around the internet at any one point in time and you try to enumerate them, that combination of source IP, source port number, destination IP, destination port number would be globally unique. Okay. All right. What's that? Oh, that's outside. Okay. Let's talk a little bit about UDP. This is just a review. There's really not too much you can say about UDP. UDP is not too exciting. It's true. UDP is no frills, bare bones internet protocol. Provides best effort service, which means UDP segments may be lost or delivered out of order to the application. UDP is connectionless, which basically means you have no three-way handshake when your data is sent. And each UDP segment is handled independently of the others. Now, UDP is used for streaming multimedia applications. It's used also by default for DNS, as we've spoken about. It's also used for SNMP, the Simple Network Management Protocol. And if we want reliability, when we're transferring data over UDP, where does that reliability functionality have to reside? In the application layer, right? This is really an application of the end-to-end principle, if you think about it. Okay. This is basically what the UDP header looks like. Okay. Only 8 bytes long. The source port number, destination port number, length, and checksum field. And so the source port number and destination port number are 16 bits long, which means what's the highest value for a port number? Not 65, so 2 to the 16 minus 1, and what's that? Yeah, 65535, correct. Okay. Then this field tells us the length of the entire UDP segment in bytes. Okay, that length field is also 16 bits long. Okay, and so what's the maximum length of a UDP segment? What's the maximum length, including the header segment? I actually asked you guys this question too in your assignment, the Wireshark assignment. Last time I asked it. No, I said it's a 16-bit field. So what's the maximum length of a UDP maximum? Including the header. Maybe I should pull up your assignment from last year. And read the line. No, seriously. You guys can work that out. How do you work that out? If that length field tells you the length in bytes of the UDP segment, including the header, and the length of the 16 bits long, what's the maximum length of the UDP segment, including the header? 2 to the 16 minus 1, right? Making sure you guys are actually awake, which doesn't seem to be the case. Now, what's that? I ask questions weird. What's that? I need to stop having classes at 8 o'clock. I actually don't have any control on when my classes get scheduled, just for the record. In years past, both lectures for this course are actually at 8 o'clock. And I realized some of my students actually told me that it didn't agree with them. What's that? Yeah, like I said, I don't agree with it. I don't. It's not up to me. And I'm getting sidetracked. But I'm making a point here. Once I went to a meeting, and this person who's now very high up in the university was saying, "Oh, we need to have classes at 7 o'clock in the morning, right?" And I was like, "Well, I have 8 o'clock classes, and the students are already struggling to get to those, telling me they'll make it to an 7 o'clock class." I think, but anyway. They point out, the same person was pointing out that social sciences has classes at, I don't know, 5 or 6 in the morning or something like that. Yes, they do, for persons who are working. Yeah. Anyway, having seen that, now back to the UDP segment. So what's the maximum length of a UDP datagram, excluding the header? What's that? 2 to the 60 minus 1 minus 8, correct? Which is 65,527. Very good. Okay. The checksum field is used to verify errors, and if that checksum field is all zeros, then it's not checked at all. The UDP datagram is not checked. The checksum is not checked. Okay. So let's talk about this notion of a UDP pseudo header. Okay. So the UDP pseudo header is used when computing or verifying a checksum, and it's temporarily prepended to a UDP message. So that it's called a pseudo header because it contains items from the IP header, okay, like the source IP and destination IP address, as well as the protocol that's carried in there. Right? Remember, every transport layer protocol is uniquely identified by a number. TCP is what? Anyone remember that? Protocol number for TCP? What's that? What's that? No, it's not 25. It's 6 actually. What's the protocol number for UDP? No, it's not. Neither 8, neither 7. No, it was 17, 1 in hex. Also, go back and look at your assignments last year. I asked you guys this. All right, anyway, the protocol number, and then the UDP header, the datagram length. Okay. So what this is used is that it's used to guarantee that the message has arrived at the correct destination. And you should be aware that the pseudo header is never sent across the internet. Okay. So the UDP checksum is used to basically detect some errors, very simple errors. So what it does is it's going to treat the segment contents as a sequence of 16-bit fields. So even with the IP addresses that I just talked about with the pseudo header, those get treated as a sequence of 16-bit numbers. An IPv4 address is how many 16-bit numbers? IPv4. 2. 2 times 16 is 32. Okay? So the checksum is computed by building a 1's complement sum of the segment contents. Right? You guys remember 1's complement? So I can compute the architecture organizations. I also saw it in my class. I know I taught you guys. Alright. So the sender will put the checksum value into the UDP checksum field. Now on the receiving side, the receiver will compute the checksum of the field. This is, by the way, a very naive way of implementing it. Okay, you compute the checksum of the received field segment, and you check if the computed checksum equals the checksum field value. If no, then you've detected an error. If yes, you haven't detected an error, but that doesn't mean that any errors have occurred. So the UDP checksum is basically computed over the UDP header and the IP pseudo header. I just talked about the IP pseudo header. And why do we cover the IP pseudo header? Because if the IP pseudo header was not covered, then there is nothing that would check that the host address was correct. Okay. Another thing of trivia, so I'm talking about UDP. There is a guy, Eggert, in a paper, stated that around 95% of all bytes on the internet are TCP, and 85 to 95% of the distinct packets that are transmitted on the internet are TCP packets. Gives you an idea of how much data is carried by UDP. Okay, so TCP rules things. Okay, so how good is a UDP checksum? Well, a UDP checksum is actually very fast computing software. Okay, you can use the same implementation for big endian and little endian CPUs. You guys understand when I talk about big endian and little endian machines? Never saw that in computer architecture? Okay, a big endian machine. Oh, how many of you read Gulliver's Travels? Yes. Okay, how did he eat eggs? What was one of the things Gulliver's Travels about eating eggs? You just remember reading the book? Well, so in Gulliver's Travels, one of the things, they went to an island and people were having a fight about the right way to eat the egg, from the big end or the little end of the egg. Hence big end and little end. And how it came into computer science is that different computers on different architectures store bytes different ways. Okay, a big ended machine will store the most significant byte on the big, first, big ended. A little ended machine will store the most significant byte last. Okay. So anyway, you're going to have the same implementation on little endian and big endian CPUs. And guess what? 16 bytes is actually not very bits is not very long, which means you're actually going to find an error once every 65,536 times, which is actually not that small a number. Okay. A nice thing is that the checksum. So the plus is a good thing. The minus bad. Okay. A plus is that a checksum can actually catch any 1-bit error. Downside, it won't catch any 2-bit errors. Okay. So if, for example, if you increment one word that ends in 0 and you decrement one ending in 1, the 2-bit errors, you won't catch that. Okay. The checksum is an option on UDP. Actually, it's not mandatory. So I mentioned earlier that an all zeros in the checksum field means no checksum was computed. Okay. And so if a checksum word gets wiped to zeros, yeah, too bad. And that's not unusual. Okay. So the nice thing is that most link layers have much stronger error detection schemes, such as Ethernet has a CRC, cyclic redundancy check. We're actually going to compute the cyclic redundancy check by hand here with this method, so it's fun. I'm leaving us the computation of the checksum because you guys did it last year. But one of the tutorial problems will actually have you compute the checksum. And this time we're actually going to do it in hexadecimal. It's a lot quicker to add that way. But the same principle. And then another thing is, say you discard bad packets, how do you ensure reliable delivery? Okay. Any thoughts on that? What's that? Well, we've answered that several times. You just push it up to the upper layer. Make the upper layer handle that problem. Okay. So now let's talk about the things that will start forming the basis of your project. We'll talk about these for the next 10 minutes. Okay. So last year when we talked about congestion of TCP, we talked about reliability, and I just told you how TCP dealt with sequence numbers and all of that. But now I'm going to talk about it so you guys actually really understand the nuts and bolts of this, and you can implement it for your projects. Okay. So We will talk, reliability is actually an important consideration at the transport and link layers. Okay. 802.11 Wi-Fi actually does some very simple reliability. And reliability is actually a top 10 networking topic. So the illusion that we have is that we have a sending process, a receiving process, and they're sending data through a reliable channel, and you inject data into a pipe, and you pull out that very same data to the pipe, and it has to be modified what you're receiving exactly what you sent. That's the illusion of what we want to have. Okay? Now, in reality, what we have is an unreliable channel. Okay? We have a channel that can corrupt bits. Okay, flip bits. She might be, doing something on the web at the same time that, I'm sending stuff to WJC with no internet, right? We're interfering with each other. So that will all contribute to the unreliable channel. So how do we get this, given that we have an unreliable channel? We're going to need to have some reliable data transfer protocol, both on the sending and the receiving side, okay? And what this will do is mask any unreliability that we have down here, okay? So on the sending side, we will call a method reliable data transfer send, okay? We'll do whatever things we need to do. Send that down to our sending side of the reliable data transfer, and then it will now call an unreliable data transfer send, okay, which sends it down into the channel. On the receiving side, we'll call a reliable data transfer receive, get the data, okay, do any checks that we have, okay, make sure there are no gaps, no bits are corrupted, everything checks out okay, we deliver the data to the upper layer with no gaps. So we have this illusion over here. Okay? All right. So reliable data transfer send is called from above, like your upper layer, application layer, or whatever. Okay? And it's passed data to deliver to the upper layer on the receiver side. Unreliable data transfer send is called by reliable data transfer protocol to transfer packet over the unreliable channel. And then reliable data transfer receive is called when a packet arrives on the receiving side of the channel, and then we call deliver data to deliver database to upper layer. Okay, so basically what we're going to be doing is we're going to build reliable data transfer protocols with increments. Okay. And for now, we're going to only consider the case where we're doing unidirectional data transfer. Okay? Now, we're going to have the possibility that control packets are going in the opposite direction. Okay? And it's actually very easy to have bidirectional data flow. Okay? You can add that quite easily. And now, those finite state machines that we studied, we now come to use them. Okay? So let's do reliable data transfer version 1. So our underlying channel is perfectly reliable, which means we have no bit errors, okay, no loss of packets. So you have separate finite state machines for the sender and receiver. So the sender sends data into the underlying channel, the receiver reads data from the underlying channel. So on the sending side, when we call reliable data transfer send and we give it some data, we then call a function to make a packet, okay, and then we call unreliable data transfer send to send a packet. On the receiving side, when we call reliable data transfer receive, okay, we extract the packet, get the data, and then deliver that data to the upper layer. It's very straightforward, okay? And by the way, in it, we basically say we just wait until we get the call from below. That means packet has come, and on the sending side, we wait until we get the call from above to say send this packet. Any questions? All right. Straightforward enough. So let's look now at where we have a channel that can flip bits in a packet. Okay? Well, we know how to deal with flip bits in a packet. The simplest implementation we can think of is to just use a checksum. Okay? Now, one question then is, how do we recover from errors? How do you recover from errors in communication? How's that? Resend? Yeah, but what happens? What's the trigger? Does it just happen automatically? Time expires? Really? You're a lot more technical than I. You think like a computer. But how do we recover from errors in day-to-day conversation, for example? You're on a timer? What do you do? Context, okay? So let's say a little more. Context. Based on what he said? You ask the person to repeat, right? That's what we all do, right? Yeah, it makes an error, right? You can't hear it, it's some error, right? Once you may try, it may not be that bad, your brain may actually be able to infer correctly, right? Otherwise, you simply say, I'm sorry, I didn't get that. Can you repeat it, right? That's not an error? What is that? Yes, that's an error. Right? When it comes to communication, it's an error, right? Which you have to handle. All right, so what does that have to do with this? It means we can have retransmissions. That's all repeating is, really. It's just a retransmission. So, what we now add, first of all, is an acknowledgement. What might an acknowledgement look like in day-to-day speech? You're talking on the phone to your friends of yours. What might an acknowledgement look like in that context? Got that? Hey, or maybe on the phone, right? Yes, yes, I got you, right? That's like an acknowledgement. Okay. What's a negative acknowledgement in the context? Let's say you're talking on the phone with your friend. Got that? Sorry? Pardon? Yes, let's be polite. Right? Pardon? Right? Oh, I'm sorry, I didn't get that. Okay? So what would happen is that the sender, when you say, I did not get that, I'm sorry, your friend should do what? Repeat what he or she has said. Right? So what new mechanisms do we need now? We need to have error detection and feedback control. Okay, so here is now our reliable data transfer 2.0 finite state machine specification. So on the sending side, we sit around, we just wait until we have a call from above to send some data. Okay, so when we get the call to send data, we make a packet with the data, add a checksum to it. We call unreliable data transfer, send, and then we transition to the state where we're waiting now for an acknowledgement or a negative acknowledgement. Okay? If we get a negative acknowledgement, what should we do? We retransmit the data. Okay? So if we receive a packet and it is a NAC, in other words, it's a negative acknowledgement, we retransmit the packet, same packet that we had just sent here. If on the other hand, we get the packet and it is an acknowledgement, then we do nothing. That's what the uppercase gamma is, and we and then we transition to the state where we're waiting to send data. Okay, straightforward. On the receiving side, we just sit around and we wait. If we receive a packet and it is corrupt, then we send a negative acknowledgement. If we receive a packet and it is not corrupt, what do we do? We send an acknowledgement and we deliver the data to the upper layer. And then we sit around and wait for another packet. Okay? That's all there is to it. Okay. So now let's say there are no errors. We're basically going to do exactly what we just said here. So on the we sit around, wait for a call from above. So we get, okay, on both sides. So we send data, okay. So we make a packet, then send the packet, and then it goes and we transition to the next state. Then here we receive a packet and it is not corrupt, so we extract the packet, deliver it to the upper layer, and then send an acknowledgement. And then we go back and receive data, it's an acknowledgement. So we do nothing and we transition to the state where we're calling for data from, waiting for a call from above. If on the other hand we get an error, so first we send the data, okay, and we so we send data, okay, and so here now we get the packet and it is corrupt, so we send a negative acknowledgement, okay, and then we've gotten a packet, it's not corrupt, it's a NAC, sorry, so we send the packet, and now we resend the packet and it is not corrupt, so we send an acknowledgement and we go back. Okay, all right. Any questions? So that's pretty straightforward. So we'll stop here for today and I'll do your quiz. Any questions going on? By the way, I have the quizzes from last week over here. And I tried to reuse paper from last week, so. I'm reading. Click on wait, keep it down. You should all be seeing the diagram. You should just have a graph, the land. All right. Flip over, you can start now. Try to follow the instructions. All right, you got 5 minutes.